Welcome to another video. We're going to be talking about the uniform convergence of a power series characterization theorem. Now, this is again more of an exercise. It's a very simple proof indeed, but we get a very powerful result. So let us have some power series like so. The standard definition. So let it be a power series. With the associated radius or convergence radius or radius and convergence r, which is greater than 0, then convergence occurs locally, uniformly, on the interval x0 minus the radius, x0 plus the radius, or if you prefer, on the open ball with the center x0 and radius r. The proof is very simple. It is essentially employ the previous theorem and everything will work out just fine. Don't worry about it, bro. Now, let us have some lowercase r which is greater than 0 but smaller than the radius. Then, by the previous theorem, that would be the power series convergence radius characterization. I shall just use the shorthand by the theorem 13.9 for x equal to x0 plus r. So if you substitute this in, which you absolutely can, you will get the following. So we have the series of an times r to n, where n ranges through 0 to infinity. And we have this, we know that this converges absolutely. Alright, now, for all x from the interval, it's a closed interval, which is important, x0 minus r and x0 plus r, or the closed ball, like so. We have that the absolute value of an times x minus x0 raised to the power of n is smaller or equal to the absolute value of an times r to n. This is trivial because this is smaller or equal to r from here. And now we actually observe, and this is interesting, that we can move this inequality, right? And in between, we can wedge the supremum over x from the interval up here, call it I, over an x minus x0. And that is because the reverse wouldn't make sense, right? This would defy the definition of a supremum. But wait a second. We know that this converges absolutely, right? Meaning the sum of these converges and is always larger than the sum of these. Thus, this sum must also converge. Therefore, we have the sum of the suprema of these summands converging. Thus, by the Weierstrass theorem, so thus, by the Weierstrass criterion, we have that the sum, or the series of an x minus x0 converges absolutely on the interval as we were talking about. Right? But this is by definition means then that this series converges locally, absolutely, on the open set that we were given at the beginning. And this concludes this proof.